Welcome to lecture number 4 on the course of electrical circuits and network analysis. In previous lecture, I have shown how to solve a network problem using KCL and KVL equation and using the DC network theorem, that is basically using superposition and Norton's theorem. So today at first I will discuss about the another DC network theorem, that is Thevenin's theorem. Okay, so this is the lecture number 4. Okay, so first I will start with Thevenin's theorem. Okay, so first consider a simple circuit with a single voltage source, and then so this is your simple circuit. This is a supply voltage V, and with this is R1, R2, R3, and this resistance is the load resistance is mentioned here, and through which we have to measure the current, that is IL, using the Thevenin's theorem. So to solve the problem using Thevenin's theorem, some steps are followed. That is the step 1. Step 1 is the load resistance is replaced by the open circuit. So if I redraw the circuit, that is basically like this. The load resistance terminal is kept at open circuit. So this is your supply voltage V, R1, R2 and R3. So now if the supply current is I flowing from the supply voltage V, and it will flow through R1, and across this point it will divide. One is flowing through the R2 and another is flowing through the R3. Now as this terminal is open circuit, okay, that means no current will flow through the R2 ohm resistance because this terminal is open circuit. That means there is no voltage drop across the R2. So that means the series current or supply current I is flowing across the R1 and R3 basically. Okay. So what will be your source current? That is equal to V by R equivalent, that is R1 plus R2. Next we have to measure the open circuit voltage from this open circuit terminal actually. So this voltage is also known as V Thevenin or Thevenin equivalent voltage, also V open circuit voltage. So as the R2 ohm is actually redundant here, that is no current is flowing through R2, that means your VTH will be same. If I measure the VTH across the R3 ohm resistance, so it will be the same across the R3. So your VTH will be basically the supply current into resistance I into R3. If we put the value of VTH, if we put the value of I, so it will be V into R3 divided by R1 plus R3. So now if I apply simply voltage divider rule here, so to find the voltage drop across the R3 ohm resistance, that is basically the supply voltage into R3 by R1 plus R3. So this is a two-way for measuring the Thevenin equivalent voltage. One is to find the source current, next apply the current into resistance to find the VTH, or simply you can apply the voltage divider rule across the R3 ohm resistance. Okay, this is your step 1. So now step 2. So your step 1 will be basically to find the Thevenin equivalent voltage, and your step 2 is to find RTH, that is Thevenin equivalent resistance. To measure the RTH, first you have to replace the voltage source with its internal resistance. As I have already discussed as the voltage source are ideal, that means its internal resistance is 0, so the voltage source is replaced by simply a short circuited path. And then from this open circuit terminal you have to measure the RTH or Thevenin equivalent resistance. So this is R1, this is R3 and this is R2. So to measure the Thevenin equivalent resistance, first what we can do? We can imagine a fictitious voltage source across this open circuit terminal. So that means from the voltage source the current is flowing and through the R2, and again from this point it will divide, one is flowing through R1 and another is flowing through R3. So that means current will divide across these R1 and R3 of resistance. So R1 and R3 are connected in parallel. With this R2 is series, so your RTH will be R2 plus R1 parallel to R3, right? So this is your R Thevenin or Thevenin equivalent resistance. Next, the final step, step 3. Step 3 is to find the IL, that means the current flowing through the load resistance RL. So to find that, first you have to draw the Thevenin equivalent circuit. So from the step 1 we have already measured the VTH, from the step 2 we have already measured the RTH. Now your Thevenin equivalent circuit will be, this is a voltage source, is known as VTH, with this one series resistance is connected, that is known as RTH, and with this the load resistance is connected. Now I have to measure the current through this load resistance, it is known as IL. So this is a simple series circuit, that means the current flowing from the source is flowing through the resistance RL, the same current. So the current will be the simply supply voltage divided by total resistance, that is RTH plus RL. So this is your the final expression of current using Thevenin's theorem. Okay. Next, if I consider the same problem which I have already used to solve using superposition or network theorem, if I consider the same problem, that is the problem was already given in my previous lecture. So there are two voltage sources are basically present, and so this was the network. So this is 10 volt, this is 5 volt, and the resistances are 5 ohm, 10 ohm and 2 ohm. So this was the network. So to solve this, first you have to short circuit the load resistance. Here I have to measure the current through this 2 ohm resistance. So your 2 ohm in the problem is the load resistance. So following the step 1, if we redraw the circuit, that means your 2 ohm is replaced by the open circuit. Okay, so this is 10 volt, this is 5 volt, and this is 5 ohm, and this is 10 ohm. So now we have to measure the Thevenin equivalent voltage across this open circuit terminal or VOC, open circuit voltage. So to measure this, if we simply apply the KVL equation here, that means the current is flowing from this 10 volt source, so it is plus, this is minus. Across this 5 ohm resistance, this side is positive, this side is negative, and across the 10 ohm, this side is positive, this side is negative, and here the 5 volt is present. Okay. So if I simply apply the KVL equation, so it can be written as 10 minus, suppose the current is I flowing from the supply voltage. So that means 10 minus 5 into I minus 10 into I minus 5, that is equal to 0. So this is your KVL equation in this circuit. So by solving this, you will find your I will be 1 by 3 ampere. Okay. Then to find the VTH, look carefully. This is your VTH. That means imagine a fictitious voltage source. Then if we apply the KVL in this mesh, that is the 10 volt with this 5 ohm, and this is a fictitious voltage source VTH. So if we put the again KVL equation, then 10 minus 5 into I minus VTH equal to 0, or we can write from the VTH, if we calculate from the VTH side, that means VTH minus 10 into I minus 5 equal to 0. The both equations are correct. Okay. So if we simply put the value of I, that means 10 minus 5 by 3 is equal to VTH, or this side VTH equal to 5 plus 10 by 3. So if we calculate both the thing, you will find your VTH will be 25 by 3 volt from the both side. If you can calculate, you will check that VTH will be 25 by 3 volt. So now the next step 2. Step 2 is to find the Thevenin equivalent resistance or RTH. So to measure this, simply the voltage source is replaced by the short circuit. That means the zero internal resistance. Okay. So if I redraw the circuit, so the supply voltage is short circuited, and the load terminal is also open now, and this is your final diagram. That means this is 5 ohm, this is 10 ohm. Now you have to measure the RTH. So again, to measure the RTH, it is the same process to measure the R Norton. I have already shown it in my previous lecture. So this is the same process. So imagine a fictitious voltage source in place of RTH. So as per the fictitious voltage source, if the current is flowing through this side, that means it will divide. It will divide. One is flowing through this 10 ohm, another is flowing through this 5 ohm. That means the 5 ohm and the 10 ohm resistance both are connected in parallel with respect to this fictitious voltage source that is present in place of RTH, like this. That means your RTH, Thevenin's equivalent resistance, will be simply the parallel combination of 5 ohm and 10 ohm, because both are connected in parallel. So your RTH will be 50 by 15 ohm. By calculating, your RTH will be 50 by 15 ohm. Okay. Next you have to measure the load current. So the step 3. First, draw the Thevenin equivalent circuit, that is basically VTH, RTH and RL. So your VTH from the step 1, your VTH was 25 by 3 volt, RTH 50 by 15 ohm, and RL was 2 ohm as per the question. This is your RL 2 ohm. Okay. So now I have to measure the current flowing through the 2 ohm, that means basically the source current, because the resistors are connected in series with this 25 by 3 voltage source. So your IL will be simply VTH divided by RTH plus RL, that means 50 by 15 plus 2. Okay. So by calculating this, you will find your IL will be 25 by 16 ampere. Okay, so your IL will be 25 by 16 ampere. So this is the procedure for solving a network using Thevenin's theorem, right? So next, the next is another DC network theorem, that is maximum power transfer theorem. Maximum power transfer theorem. Okay, so that is, from a given network we have to find out the maximum power. We have to obtain the maximum power, and what is the maximum, what is the condition to achieve the maximum power from the given circuit, and what will be the maximum power. So in this question we have to find out. So first, if I consider the same circuit that is already used for solving the Thevenin's theorem, the same circuit, this is R1, this is R2, this is R3, and this is the RL. We have to find the current through this RL. This is your V. So to solve the problem using maximum power transfer theorem, the step 1 and step 2, that is similar like the Thevenin's theorem. That means your step 1 is to find the Thevenin equivalent voltage, that is to find VTH, and your step 2 will be to find RTH. So this is basically similar like the Thevenin's theorem. So I am not going to repeat all those things. So state, I will measure the load current. So that expression is also same, that is VTH by RTH plus RL. Okay, this is the expression of load current. And what will be the power? Your power is basically IL square into RL, that is the load current square into load resistance I square R. So if I put the value here, so IL, that means VTH square divided by RTH plus RL whole square, that is your IL square into RL. So this will be the expression of power. Next, we have to find out what will be the condition to obtain the maximum power from the given circuit. So to find the maximum condition, so what we can write from the our previous knowledge of class 11 or class 12 science, that is to get the maximum condition we have to derivative, the first order derivative, the equation of P with respect to whom? With respect to the variable load resistance, because this resistance is variable RL. So to achieve the maximum power, to obtain maximum power, so you have to first order derivative the expression of P, maximum power, with respect to whom? With respect to RL, that is dP dRL is equal to 0 to achieve the maximum power. So that means d dRL of your P will be, I have already calculated the expression of P, that is VTH square divided by RTH plus RL whole square into RL. So this is basically the expression of P. So dP dRL is equal to 0 as per the condition. That means what will be the solution? Simply RTH plus RL whole to the power 4. So derivative method is U by V method, that is in denominator, that is V square, and in numerator that is V into U dash. So RTH plus RL whole square into U dash, that means VTH square into RL. If I derivative this with respect to RL, so it will be only VTH square minus U into V dash. So what is your U? That is VTH square into RL into V dash, that means RTH plus RL whole square. If I derivative this thing with respect to RL, it will be twice of RTH plus RL. Okay, so that is equal to 0. So from this condition, simply you can write RTH plus RL whole square into VTH square, that is equal to VTH square RL into 2 RTH plus RL. Okay, again the VTH square will be cancelled out, and this RTH plus RL, this 2 degree power will be cancelled out. So from this equation, if I solve this, RTH equal to RL, because RTH plus RL and the right side will be twice RL. So by solving, we get RTH equal to RL. So this is the condition for obtaining maximum power, RTH equal to RL. Then what will be the maximum power? This is the condition. Then the maximum power will be P max will be by placing the condition, that is RTH equal to RL. So what we can write? VTH square by, if we substitute the value of RL with RTH, that means RTH plus RTH whole square into RTH. Okay, because RL is replaced by the RTH Thevenin equivalent resistance, so it will be VTH square by 4 RTH. So this is the expression for maximum power. So the condition for maximum power was the load resistance will be equal to the Thevenin equivalent resistance, and the maximum power will be VTH square by 4 RTH. Okay, so if I consider the same problem that I have already solved using Thevenin's theorem, because the step 1 and step 2, that is the Thevenin equivalent voltage and Thevenin equivalent resistance, VTH and RTH are as similar as Thevenin's theorem to solve a network using maximum power transfer theorem. So now if I consider the same problem which I have already solved using Thevenin's theorem, from this we have got VTH was 25 by 3 volt and RTH was 50 by 15 ampere, and the RL was given 2 ohm. So as the process of finding VTH and RTH are same as Thevenin's theorem, so I am not going to the detailed calculation again. So straight I am going to the maximum power. So what will be the maximum power? So by placing the RL equal to RTH, so it will be VTH square, that means 25 by 3 whole square by 4 into RTH, that means 50 by 15. So by calculating this, you will find your maximum power will be 125 by 24 watt. So it is near about to 5.208 watt. So this is the maximum power following the previous circuit. Okay, so let me check the same problem using a simulation, using a MATLAB simulation, whether if I vary the load resistance, because to achieve the maximum power I have to set the load resistance is equal to the Thevenin equivalent resistance. But if I set the load resistance less than the equivalent resistance or greater than the equivalent resistance, I will not find the maximum power. So that thing is must verified by the simulation. Okay. So if I go to the simulation, so this is the same circuit and the 2 ohm is the load resistance. So across this, now I have measured the load voltage and the load current. So if I simply product the load voltage and load current, I will get the power. So first the load resistance was set as 2 ohm as per the problem. So if we run the simulation, it will show the power is 4.883. So the maximum power was calculated at 5.208. So next, that means the load resistance is less than the R Thevenin, that is 50 by 15. If I solve the 50 by 15, it will be approximately 3.33 ohm. So here the load resistance is set as less than the RTH. Next, if we set it as greater than the RTH, suppose I set it as 5 ohm. Okay. Then if I run the simulation, so I get the power is only 5. Okay, 5 watt. Then if I put it the Thevenin resistance here, that means 50 divided by 15. Okay, so if I run the simulation, it will show 5.208. That means this is the maximum power. So by putting the load resistance is equal to the Thevenin equivalent resistance. So that means your theoretical calculation and practical is again validated in the simulation platform. So this is the procedure of solving a network using Thevenin's theorem and maximum power transfer theorem. Okay. So now if I talk about the efficiency, how can I calculate that? Let's see. We have already determined the power delivered by the load, that is equal to the load power, which is also called the output power basically, that is equal to IL square into RL. Now the power delivered from the source, which is represented by PS, it is actually the input power. Okay, that is equal to IL square into total resistance, which is equal to RL plus RTH, the total resistance. Now the efficiency will be the ratio of output power and input power. So percentage efficiency will be P out by P in into 100%. Now if I put the value, so which is equal to IL square RL divided by IL square RL plus RTH into 100%. So efficiency actually represented by the symbol of eta. So now by following the maximum power condition, if I put the value of RL equal to RTH, so now the eta will be IL square RL by 2 IL square RL. So it is actually, but IL and IL square and RL will be cancelled out, and it is exactly the half, that is 50%. So that means in a circuit applying maximum power transfer theorem, the efficiency is always remains same, that is equal to 50%. Okay, so with this I am ending the today's lecture. Thank you.